Go team. So now I'm going to be talking about dissociation energy and overtones. So we just finished the combining the harmonic and or looking at harmonic and anharmonic modeling of vibrational modes. So now what we've got is I've taken the anharmonic potential, and I'm now going to explain the differences between the different types of dissociation energy. Okay, so let's start with the first one, this DE. This is the wave number associated with the dissociation energy, but notice it goes down to the bottom. Do you remember what that is called? Right, 0 point energy. Hopefully you said it out loud. If you didn't, pause me, go back and be like, 0 point energy, and go team. Anyway, okay, so it's late. So this dissociation energy is the classical dissociation energy. Okay, or you can think of it as the depth of the well. And you can learn a lot about your 0 point energy by understanding your classical dissociation energy and its relation to the molecule. Okay, the next one is going to be this. So if we go from V0 up to the dissociation energy, so now we have D0, and that equals the experimental dissociation energy. Okay, so if you want to know the difference between, or if you want to look closer at the relationship between D0 and DE, you can say that DE is equal to D0 plus 1/2 HV0 minus 1/4 HV0 XE. Go team. So you can relate, you should all be, yeah. So where this is your anharmonic constant, that's your fundamental frequency. So what you can do is you can say, all right, well, I know that D0 plus then 1/2 HV0, so there's that one, minus then this value is going to tell you how much this changes based on, so there's going to be a very small amount here that you're subtracting off based on how anharmonic your molecule is. Go team. Okay. So how do we get that information? Well, remember what I told you that in the harmonic model, you can have transitions that are plus or minus V is equal to, so +1. So you can have, so you can have between 0 and 1, 2, 3, 1 and 2, 2 and 3. Cool. Overtones are when delta V is equal to +2 or +3. And so you can have one of the overtones, a very popular one, is from 0 to 2. So this is called the first overtone. And then from 0 to 3 is the second overtone. If you have a really anharmonic system, you actually have enough of a variation when your Hamiltonian operates on your wave function. Don't forget, when this equals 0, this is the transition dipole moment operator expectation value. When this equals 0, you don't have you have a forbidden transition. It happens that when you have overtones, or sorry, when you have anharmonic, that's a big mass on a spring. So M1 and M2, when you have an offset in your masses, so you have an anharmonic oscillation, the transition dipole moment operator becomes non-zero very weakly. So it's a very small number, but still non-zero when you have a transition from 0 to 2 and 0 to 3. It's a little bit bigger for 0 to 2, slightly smaller for 0 to 3, and it gets smaller and smaller as you go down, or as you go farther into the overtones. Okay, so what's really cool about the overtones is you can learn a lot about your system in terms of how anharmonic are you. Neat? Let me show you. This is falling off. There we go. Okay, so due to the overtones, hope I didn't ruin the whiteboard. I used some regular cleaner stuff that I have, and I don't think it worked very well. Okay, so when you have this picture again, the idea would be that how large is the dissociation energy? D0 equals what? Well, it should be that if you just add up each of these, oops, you should be able, if you just sum all of these, you should get, so this is your vibrational term, you should get that. Go team. You just add them up, that plus that plus that plus that plus that. But the thing is that getting these numbers isn't the easiest thing to do. So you'd have to look at the overtones to do it. And so you can say that G of V plus 2, which would be your first overtone, minus your, so basically this one minus this gives you that. If you draw the picture and look at what term, which term represents what, it makes a lot more sense. So if you want to determine what that size is, you take the first overtone minus the fundamental transition, first overtone minus fundamental transition, and that gives you, well, it gives you a value, but then you can relate that value to a Taylor series expansion, of course. So the difference between those gives you information, one on your oh, you can't see that, I'm so sorry. That should read 2V plus 3 anharmonic constant frequency plus, and then the next term. So if you look on, I'm in 11C, by the way, or 12.10. So this is looking at the wave number overtones associated with getting that value. Okay, now there's going to be fluctuations in this. There's not a systematic decrease, and that's what we're trying to find, is what's that systematic decrease of how those vibrational states get closer and closer together. Okay, so then what you can do is you can determine what each of these values are, and then instead of just adding them together, a more accurate way to do that would be to plot them to where you have the change of G for V plus 1/2. So that would be each one of these. And so this would be the 1/2. So this would be your G value. So this is V plus 1 plus 1/2. So when V equals 0, you have 1/2. When V equals 1, you have 3/2. So then you have, so when you determine what your V equals 0, your G value of 1/2 is going to be that. And then you're going to determine that. And if you then plot out what each one of those are, it's going to turn out to be linear. Team? So, and if you think about this, this is the bigger one, and it gets smaller and smaller as you go up. Go team? Okay, so when you're up here, it's going to be really small, so it's probably going to be around there. So then what you do is you have the equation for the line, and then you want to basically determine what all of these values would be. So you integrate that, and you find the area under the curve, and that is going to give you D0. Awesome. So this is called can I remember the name? Burge-Sponer plot. You'll be using that to determine the dissociation energy of your overtones of the HCl and DCl problem. Sweet. So much stuff you can learn from spectroscopy. Okay, I think that's all I want to say on vibrational. The other thing I would say is that, nope, I think that's it. Next video, I'll talk about coupling. Bye.